Swayam Prabha. Digital India. Educated India.
Okay, so today we will in today's class, after having looked at bus bar and transformer protection, we continue our series on unit protections, and we will look at generator protection, the next apparatus in our list, that is the generator protection. Now, with generators, quite a few of the principles are similar to what we discussed, like differential and all that, but there are a few other nuances like out of step and loss of field, etc., that have to be considered. So, we will look at them. So, today's class is on generator protection. Now, there could be, as I said, a few nuances like other than the faults itself, there could be some conditions known as adverse system interaction, like you say, like the generator, because these are, we are talking specifically of synchronous generators, they could lose synchronism, that is go out of step, and these can cause large variations in voltages and currents, which could even damage the generator permanently. So, they also have to be protected against. So, they are since we began with the differences, so I listed it first, but other than that there are abnormal operating conditions like for all equipment. So, you will have under this, you will have overloads, over voltages and other conditions like we have been discussing so far. So, here we have say the first one is obviously overload, then we have over voltages, then then a peculiar thing is loss of field. As we know, a synchronous machine is a doubly excited machine. So, the field also has to have DC excitation, that could be lost, though it can work as an induction motor. We will see how that could cause a problem. So, we need to protect against that as well. Then there is unbalanced operation. So, loss of one phase, single phasing, etc., or could be even large imbalance in the loads on each phase. Okay. Then low frequency or under frequency or over frequency. So, we will classify it under one head only. So, one more is loss of prime mover power. You need mechanical input to the generator, that could be in the form of steam turbine for steam and gas generators or even nuclear powered generators, but for hydro generators it could be a hydro turbine. So, if that is lost, then the generator could go into motoring mode. Okay. So, we need to protect against that also. Then we have This could of course come under adverse system interaction also, the subsynchronous oscillations. The issue here is that for subsynchronous oscillations we do not, I mean the relays are strictly not what we have studied so far. Those are more mechanical type of relays which detect the torsional vibration. So, they are torsional relays, and unless the generator is very large and or there are some very specific instances or by simulations that it is determined that there are subsynchronous oscillations, those are not provided. So, we will, though we have listed it, we will not discuss it in this. Okay. And there could be an out of step condition also. Condition which will be under adverse system interaction. Now, the first of course, for large and medium and large generators, the first type of protection which will be provided is a differential protection. Okay. Under differential protection, that is, it is usually known as 87G. If 87 is our device number for differential relays, and G is of course for the generator. Many a times there is no separate generator circuit breaker provided. So, it could be for small and medium units, generator and transformer together could also be provided on an overall differential, in which case it is labeled as 87TG. But we will look at only specific generator protection here and differential protection of generators. The generator of course could be star or delta connected. We will look at the star connected generator first, which we will draw so that it is easier to understand, and then I will show a picture of the similar thing for a delta connected generator. Okay. So, first we will draw the generator. So, these are the three windings of the generator, may be labeled as A, B, C. Or RYB as is convenient. So, they are connected in star. Okay. Generators may not be solidly grounded, but here for the sake of convenience we are just assuming that this generator is solidly grounded. It otherwise could be, if there is a neutral grounding resistor or a reactor, then it simply you have to add a RG or ZG, as the case may be. Okay. So, since this is a this star connected generator, the CTs also will be connected in star. We will connect them. These are the CTs, and our dot convention will remain the same. We will, this is a connection here, and okay. So, this is the star point and they will be connected, and this is grounded. Okay. Now, just for the sake of drawing, this will be connected to the A phase CT. okay, and these are the restraining coils. The operating coil will be connected between, this is the operating coil. Okay, similarly, similar connections will be made for all the other phases. We still have to show the operating coils, but we will do that shortly. Okay, and the other end of the coil we will have a common connection like this. Okay, so this is how the operating coils will be connected. So these are the restraining coils. This is the dot convention. So it enters here, leaves here, enters here, leaves here, enters here, leaves here. So if you have IA, IB and IC, you will have IA, IB and IC, and this convention will also be similar. These are the dots here. So since it enters here, it will be leaving from here. Okay, so same direction here, IA, if there is no internal fault, of course, IA, IB and IC. Okay, so this completes the differential relay circuit. Now, here while setting it, it is similar to a biased percentage bias differential characteristic like we have seen, but the slope could be lower, as there is, you do not have problems of magnetizing in rush and no load current and all that in the case of generators, unlike that of transformers. Also, care has to be taken to see that these CTs are properly matched, so that there is no so that you could set the percentage differential accordingly, or the percentage bias accordingly, so at a lower rate. Okay, so for a delta connected generator, we will quickly, instead of drawing it in the interest of time, we will quickly see a slide. So here we can see that this is a delta connected generator, similar to the star connected generators. Here the difference is that you can see here that the CTs, which you can see here are placed in the inside the delta. Okay, so that and then this they are hardwired such that you get IA minus IB flowing in this you get IA minus IB flowing in these restraining coils. You get IB minus IC in these coils and IC minus IA in these coils. And while these are straight away connected in star, so that the same current will flow. Okay, the CTs on the outside or in the line. Okay, so you can see that since IA minus IB flows here too IA minus IB will flow, and in case there is no internal fault, in the current in the operating coil there is no current in the operating coil, or it is almost 0. So here too the CT matching and all that has to be correctly done. one difference here between electromechanical, static and numerical relays is, in numerical relays you could just these CTs also you could connect in any fashion, and then just since IA, IB and IC are available, you could just do IA minus IC. You need not hardwire the CTs and the relays in a particular fashion to get IA minus IB, IB minus IC, IB minus IC and IC minus I. Okay, unlike in electromechanical relays, you will have to do all this hard wiring. So numerical relay saves some complication there also. Okay, so this is about differential protection. Then we go to the overload protection is 50-51 is more or less similar to all other equipment that we have seen so far. For ground fault protection, this is a little different. So let's see that stator ground fault protection. So most stator ground faults, are a result of insulation failure. Okay, so they start off as some puncture in the insulation or something, but eventually they could these incipient faults could turn into could rather lead to turn faults, or even if there is a complete failure of the insulation, could also lead to a ground fault. Okay, so this could lead to or ground faults. Hence, protection is essential. Okay. So, the for a generator usually, and for most rotating machines, some grounding impedance will be provided in interest of limiting the fault current or the ground fault current, because as we can see here, it could lead to these turn to turn or ground faults if the fault current is very high. So of course there is a trade off which we will see shortly, but an impedance grounding is provided, high impedance grounding, or the second is of course low impedance grounding. Third is hybrid of high and low. So we all know that the ground fault current, say there is an A phase fault, is 3 EA upon Z1 plus Z2 plus Z0 plus 3 Zn, or this Zn is the impedance in the neutral of the generator. Now to reduce this fault current, these are of course generator parameters, but we could increase Z and then reduce that. So if this Z is sufficiently high, then this could also this fault current could be limited to even 1 to 10 amperes. Then it becomes a high impedance grounding. But the problem with this is that you do not have sufficient current to clear the fault in a very short time. So, the sensitivity of the product protection or the ground fault protection reduces. To avoid that, you could reduce the impedance, grounding impedance, and provide a low impedance grounding. But then of course, the fault current would increase slightly, which can be tolerated, which have a slight increase in fault current, but also not so much as to damage the stator permanently or something like that. So, with low impedance grounding, one very commonly provided scheme is sort of a differential scheme. So, let us see that quickly. Just drawing the generator again. The phase A, B and C. Okay, and this is grounded through an impedance Z. Okay. So, the CTs will be provided like this. This is the earthing symbol. So, there will be a CT and a sensitive earth fault rate 51 OG, or let us leave it at 51 only, and then this is these are phase fault relays. So, 50 or 51 as may be phase relays. Okay, and now this is connected in a sort of a differential connection. Okay. And the 3I fault current, say I am just labeling it as I, will flow like this, and if this is a dot convention, and let us assume that it is flowing like this. So, you will have a current flowing here, and since this 3I will go through here and this convention is like this, you will have okay 87 G or OG. Okay. So, this the current in the two coils here will be opposite, and then it will not. For an external fault, there will be no trip issued. Okay. However, for an internal fault, both these will be in the same direction, and then this will provide a very sensitive earth fault protection. Okay. So, the next protection we will move on to is reduced or loss of excitation. Okay. Now, as we discussed in the beginning, a synchronous generator is a doubly excited machine in which you provide a DC excitation to the field. Now, if there is somehow a loss of or even a complete loss of excitation would lead to operation like an induction generator. But even if there is partial loss of excitation due to any reason, then the system will have to provide the reactive power to the generator. And the issue with most turbo generator is that the leading power factor capability is limited. Okay, you can see it from the capability curve. So, the x axis is the real power, the y axis is the reactive power axis, plus MVR means it is supplying power to the system and it is operating at a lagging power factor. Minus MVR means it is absorbing power from the system and it is operating at a leading power factor. As you can see that there is it is not symmetrical, So, there is first of all you will have the SSSL or steady state stability limit. Okay. So, when the generator operates at high leading power factors, there is a possibility of it going unstable. So, you have this curve which cuts it and forms what is known as the steady state stability limit. Also, if we were to ignore that, if at a very reduced level of excitation there is a problem of the end windings, okay, the flux, because it concentrates there, the problem of end windings getting heated beyond their capacity. So, you have a stator end winding limit also. Okay. So, all in all we can see that the reactive power absorption capability, or in other words the ability of the synchronous generator to operate at leading power factors is quite limited. And so, a protection has to be provided to the generator to sense this loss of field or reduced field. Okay. So, at some level of reduced field operation or some level of leading power factor operation can be tolerated. So, the protection system should raise an alarm if reduced excitation is detected. Okay. Or if it persists or complete loss is detected, then a trip is issued. Okay. If this condition persists, because though we saw the limits and all, the operation at leading power factors can be tolerated for some time, but if it persists for a long time, if this condition persists, then a trip is issued or a trip command is issued. So, first raise an alarm, the operator can look into why this alarm has been raised, and if there are some ways in which he or she can rectify the situation. If that is possible, then there is no need to trip the generator, because tripping of a generator is a big event. If it can lead to a lot of other complications and so on. So, first an alarm is raised, and then if the condition persists, then only a trip will be issued. So, to achieve this, distance relays are used. Okay. Distance relays, in the sense they are not now measuring, we are not using the same application as such as a line protection, because they are not looking into the line and though they measure the apparent impedance, they are not looking at zones of protection and and such other such settings associated with lines, but they are basically what we are saying is we are using impedance relays, okay, and they are installed at the generator terminals. And directionally they do not look outward towards the network or the system, they are directionally looking into the generator. Okay. Now, this capability curve that we saw, because now we are talking of distance relay, so we need to visualize this, or to think of the characteristic on an Rx plane. So, so the capability curve of the generator which we just saw is interpreted on the Rx plane. Okay. If the complex power, because we are talking in terms of power, so is P plus JQ, then the ZAP is we saw this when we looked at load and load encroachment with distance relays. So, similar kind of derivation. Sorry, this is not P plus JQ, this is P square plus Q square into P plus JQ. Okay. So, we will look at the relay characteristic now. This is how when you, so that is why these two figures have been placed side by side. So, you can see here that this is how the this is the impedance, the outer and the outer green circle and the inner red circle are the impedance relays, okay, or the distance relays as has been mentioned here. These are the settings. You can see it's mentioned on the diagram. The x axis is the R axis, and the y axis or the is the impedance axis or the reactance axis, x axis in terms of x. So, R and x. Okay. So, we could also use a directional unit. Okay. Coming back to the distance relay settings, the inner circle will protect against complete loss of excitation. Okay, this one, the red circle here will protect against complete loss of excitation. So, the relay will operate, the impedance relay, the impedance is somewhere here, see the normal area of operation is here between these two lines, okay, between this line and this line, okay, it is somewhere here, and this could if there is a complete loss of excitation, the locus, the impedance locus could move into the will move into the inner circle, depending on whether there is complete loss of excitation or only partial loss of excitation. Okay. So, if it moves here, then the operating time of about 200 to 300 milliseconds is given to shut down the generator. Okay. The diameter of this circle is of the order of xd. Okay. Xd is the direct axis reactance of the generator. So, this diameter is of this circle is of the inner circle is xd. Okay. And the offset, okay, the upper part of the circle is about 50 to 75% of xd dash. Okay. The transient reactance below the origin by 50 to 75%. Okay. So, this one the outer circle will be will be for partial loss of excitation. Okay. Now, here if you can see, if you if it can be observed that the steady state stability limit is also plotted on from the capability curve. It is also plotted on the Rx plane also. So, the offset for that is given by the radius is given by of that circle v square upon 1 by, I am sorry, this is q. Okay. So, that completes the loss of excitation protection. It is a very important protection to be given. That is why we discussed it in a bit of detail. Okay. Similar to I mean the relays are similar to distance relays, but this is how the setting is done. Okay. The minimum excitation limit and the steady state limit are also plotted here. Now, the rest of the protections are we will discuss in for the sake of completeness of this discussion. These are the important types of protection. The others are of course not unimportant, but we will discuss them in brief. So, protection against unbalanced operation. Okay. So, most if you see most generator transformers will have R of the vector group delta star, okay, and with delta on the generator side. So, now what is the consequence of this connection? That if there is an unbalance, operation due to whatever reason, if there is a single phasing or even the loads in the three phases are different, then you will have, for a completely balanced operation, you have only positive sequence currents flowing. But when you have unbalanced operation, you have both, you have all components, positive, negative and zero sequence. Now, with this delta, the zero sequence current are trapped in the limbs of the delta. So, only positive and negative sequence current will be observed on the generator side. Positive sequence currents of course are there doing balanced operation, and it is a normal kind of operation when there are only positive sequence. So, they will not cause any issue. But when negative sequence current flows, what will it cause? It will cause a negative sequence field or a rotating MMF in the opposite direction at synchronous speed. Okay. So, the difference between that causes change of flux linkages in the rotor, and a negative sequence currents will be induced. Now, this will cause heating and could lead to the damage of the generator. So, there is according to ANSI standards, there is a negative sequence withstand capability of a generator, which is given by I2 square T is equal to K, some constant. Okay. Now, this I2 is the negative sequence current in the generator, negative sequence current in the generator. Now, so negative sequence relays are provided, and the setting is usually of the order of 5 to 50%, but keeping this in mind, they are usually set to around 8%. So, it can tolerate a negative sequence component of about 8% of the total current. So, this is how the negative sequence current setting is made for the generator. Now, we go to the next protection, which is the generator motoring. Okay. So, when does this happen? If there is some reason there is a removal of mechanical input. So, what would happen? The rotor MMF wave will drive the rotor. Similar to an induction motor. And the generator will go into a motoring mode. Now, why is this harmful? It can damage the steam turbines. So, can damage the turbine. This could lead, because if it is motoring, then the turbine is not designed to operate in the reverse direction, damage the steam turbines. And for hydro turbines also, it could lead to cavitation. Can lead to cavitation, which could also damage the turbine. Okay. So, you need to protect against this kind of operation. This is done by providing reverse power relays. Okay. So, this sensitivity is about can tolerate about 0.5%, 0.5%, and time delay is about usually of the order of 2 seconds. Okay. The next one is over voltage protection. So, this should be fairly straightforward. Over voltage, again, it need not trip the generator immediately. If there is an over voltage of the order of say 110% or 1.1 pu, then there is an alarm. You do not trip it immediately, and trip if it persists for about 1 minute. Okay. This timer is of course settable. Then if this exceeds, if the over voltage exceeds say 120%, then trip in a few seconds, maybe 5 or 6 seconds is okay. So, why can why could this happen? It could, of course, the consequences we will see shortly. There could be many various reasons, So, the voltage at the generator terminal voltage, if this is a generator and this is its synchronous reactance, and this is the terminal voltage Vt, and this is the open circuit voltage. The is controlled by an automatic voltage regulator. Okay. So, it takes the input from the terminal voltage as a comparator here. Okay. And has a reference input here, Vref. Okay. And it regulates the field current to control the open circuit voltage. So, terminal voltage is controlled by an AVR. by this AVR here. Okay. So, if load reduces, so if say the load current reduces or the load reduces, so the AVR will reduce, the field current, so as to reduce the open circuit EMF E. Okay. So, but if this is incorrect, if there is some incorrect operation due to some reason or incorrect setting, then if this doesn't action doesn't happen, then it can lead to over voltage. Okay. And some issues in setting or incorrect operation can lead to over voltage and consequently overfluxing. It's directly the flux in the core will directly be proportional to the voltage. So, it will not only lead to overfluxing in the generator, but also the connected transformer. Okay. And that can of course cause large magnetizing currents. Flux patterns that are unacceptable. Okay. So, it could lead to large magnetizing currents, flux patterns that are unacceptable, and this could lead to overheating. So, this has to be protected by an over voltage relay. The next protection that we provide is V by F protection. V by F is similar to the over voltage, because V by F will also lead to overfluxing. Why is that? From the EMF equation we know E is equal to 4.44 phi m F n. So, phi m is E by F or V by F. Phi m is proportional to V by F. So, during startup and shutdown, the speeds could be different from nominal speeds. And it could cause overfluxing, which would again lead to the similar problems as over voltages. Okay, large magnetizing currents, flux patterns that are not acceptable, and overheating. The next protection that is provided is out of step. So, we saw some part of out of step when we saw distance relays. So, but in this case a slight different discussion, or slight if we could say addition to that discussion is, now modern generators have high XD, and the EHV connected EHV networks have lower and lower impedance, have low reactance. So, this could it is likely that the electrical center. We discussed the concept of electrical center when we discussed distance relays. Could be within the generator transformer, generator transformer. Okay. So, we saw what happens when when the electrical center occurs, the machine is out of synchronism, and it could lead to very high voltages and currents. So, to protect against that, a distance relay looking into the generator or generator transformer should be installed. Okay. So, we could make use of the same relay. So, since it is a distance relay, we could make use of the same relay that is installed for loss of field. So, which will pick up on such conditions. On out of step. So, if the swing moves out, or the swing meaning the impedance locus moves out before the timer runs out, then there is no trip. However, on the other hand, if it stays within the relay setting for more than the timer duration, then there will be a trip issued. Now, we have completed the important protections that are to be provided for the generator. Only we have not made a distinction between conventional relays and numerical relays or numerical protection, because you could use either relays. Only one place in the differential we mentioned that the hard wiring need not be done. Okay. So, this could be numerical protection could be done in time domain or frequency domain. Time domain meaning you could do a sample to time sample comparison. Okay. Sample to sample comparison. However, here there is a danger of maloperation if or if accuracy is compromised and you desire a very fast operation in quarter cycle or so. It is generally based on a pooling method. If the difference in the samples persists for a certain number of pooling cycles, only then a trip will be issued. So, there will be a slight delay, but at the you will gain in accuracy. If you are talking of frequency domain, that is we use normal phasor estimation methods like full cycle DFT or half cycle DFT. We have to take care of the DC offset, because this is a generator, and if there is a fault, there could be a DC offset current. Okay. So, if you are using full cycle DFT, then you can approximate the DC offset current by a DC signal. Okay, which would mean that the full cycle DFT, the DFT will reject it, and you will get only the fundamental will reject it. But if it is a half cycle DFT, this is not possible. So, you will have to use a mimic impedance. So, half cycle DFT, I mean a relay based on a half cycle DFT, you will have to use a mimic impedance, because this will not, this rejection of the DC offset will not be possible. Okay, so now with this we close our discussion on generator protection, and next time we will see motor protection, and then that will be the end of the course. Thank you.